Okay, so unfortunately YouTube limits the length of videos to 15 minutes. So I'm going to have to break up this lecture into 5 parts. So last time we learned about the indefinite integral, which is basically undoes differentiation. So the antiderivative of some function lowercase f with respect to x is going to be some function capital F, where the derivative of capital F is lowercase f. So last time we were learning about these different rules of integration. And the first rule was the integral of a constant with respect to x is going to be k times x plus some constant c. And we can make sure that this is the case and check ourselves by differentiating the right side with respect to x. And we get k, which should match up with the integrand of the left side. And c here can be any number because we can have an infinite family of functions which are the antiderivative of k, which are basically just vertical shifts of each other in terms of the graphs. Okay, so that was the first rule. The second rule was the power rule. The integral of x to the n dx is 1 over n plus 1 times x to the n plus 1 plus c if the exponent n is not -1. And the missing case was the integral of x to the -1 was the natural log of the absolute value of x plus c. And we can check that if we differentiate the right side here, the n plus 1 comes down, cancels with this 1 over n plus 1, so that the coefficient becomes 1, and we keep the base the same, reduce the exponent by 1, and we end up with x to the n. And in this case, we learn that the derivative of the natural log of the absolute value of x is 1 over x. Okay, so we one technical thing, either side only makes sense when x isn't 0. So that's what we talked about last time. Now let's learn about some new rules. So the first one is, what if we're trying to find the antiderivative of some constant times the function? How does that relate to the antiderivative of just the function itself? Well, we have a rule that tells us that the derivative of a constant times a function is just the constant times the derivative of the function. And so undoing that basically says that we get the constant times the antiderivative of function f. So that means we can pull constants outside of this integral symbol. And so, yeah. Now, what about the integral of the sum or difference of two functions? So if we were trying to take two functions, f and g, and we add them, and we want to find their antiderivative, what will it be? Well, if we had an antiderivative for f, and we had an antiderivative for g, and we added them, then we would get a function whose derivative would be f plus g. So this is going to be the same thing as the integral of f plus the integral of g. So just like differentiation, we're trying to integrate the sum of two things. We can split apart and can only find the antiderivative or integrate each of them individually. And similarly, if we have the difference of two functions, basically because of this constant multiple rule. Just making sure. We also have the exponential. The integral of the exponential function, base e exponential. Base e exponential. The antiderivative is going to be just e to the x plus a constant, because the derivative of the right side is going to be e to the x plus 0. So here we go. Okay, so now we have this basic set of rules that's going to allow us to do a large number of integrals, to find a large number of antiderivatives. So let's do an example. For example, let's integrate 7 plus 8 t squared dt. And let's do it in painful detail so we can understand how these rules help us do the problem. Okay. Now we're trying to integrate the sum of two expressions. So rule number 4 tells us that we can do that by just integrating the first one and then adding to that the antiderivative of the second one. So now we get the integral of 7 dt plus the integral of 8t squared dt. Well, let's see. We keep the first one the same, and now rule, let's see, the constant multiple rule, rule 3, that's what I called it, tells us that if we have the integral of 8 times something, we can pull the 8 outside and just have this be plus 8 times the integral of t squared dt. Now, we also had rules that, let's see, we had a rule that gave us the antiderivative of a constant. It said that the antiderivative of 7 would be 7t. We're integrating with respect to t here, so the antiderivative of 7 would be 7t plus a constant, and I'll call it c1, where the 1 is called a subscript. It's below and to the right of the variable. That way I can have as many constants as I want. I can have c1, c2, c3, and they're all perhaps different numbers. We also have, then we have plus 8 times the antiderivative of t squared dt, and the power rule tells us that the antiderivative of t squared dt, let's see, that was rule 2, told us that that was 1 over 3 t cubed plus a constant, because if we were to differentiate this with respect to t, we would pull down the 3, which would cancel with the 1/3. So then we would reduce the exponent by 1, so we only get t squared, and the derivative of this constant c2 is going to be 0. So we end up finding that the answer will be 7t plus c1 plus 8 times 1/3 t cubed plus c2. And if we combine c1 and 8 times c2 into some other constant c, we'll just get 7t plus 8/3 t cubed plus c. So 7t plus 8/3 t t cubed plus c. And if we want to check that this answer is correct, we can just differentiate that with respect to t. And make sure that we get the integrand that we started with. And we'll just get 7 plus 8/3 times 3t squared plus 0. And algebraically, 8/3 times 3 will just be 8. So in fact, you do get the integrand back. So we have done this problem correctly. Now let's try a more challenging use of the power rule. Let's take the antiderivative of 3u to the 3/7 du. And I'm using different letters here just to get you used to using different letters. And the fact that this d whatever here is actually important. It needs to match up with whatever your variable is. Okay, so the constant multiple rule tells us that since we're trying to find the antiderivative of 3 times an expression, du, that we can pull that constant outside and have this, and this is the same as 3 times the antiderivative of u to the 3/7 du. And then so now we have 3 times the antiderivative of u to to a power, which is just a number. And we know how to do that is using the power rule. So u has to, so now the exponent would be 1 plus 3/7. So it will increase by 1. Write this larger so you can see it. And 3/7 plus 1 is just going to be 10/7. And we need to make sure that we put the reciprocal of 10/7 out in front. And the reciprocal will be 7/10. And the reason for that is if we want to differentiate this bottom thing with respect to u, then we would bring down the exponent 10/7, and we would want it would appear in the front here, and we would want it to cancel with 10/7, or sorry, 7/10. Alright, so that's why we use the reciprocal. And then we have plus the constant, and if I call it C1 and then multiply through by 3, we end up getting 21/10 times u to 10/7 plus some other constant c, which I'll just call c. Or I could call it d if I wanted to. Okay. So we take the antiderivative of 3u to the 3/7, we pull out the constant, and then apply the power rule by increasing the exponent by 1 and adding a coefficient, so that when we bring the exponent down, we will eventually get a coefficient of 1 back. And then we multiply this out. And we can check this. This is correct by differentiating 21/10 u to the 10/7 plus c with respect to u. And we would get 21/10 times 10/7 u to the 3/7 plus 0. And the 10s would cancel, and 21/7 is 3. So we in fact get back exactly what we wanted.